Hey guys, so I'm just gonna make this video for anyone who has any questions about the high school chem practice. So for those who don't know, this is what we're gonna be doing in our labs next week if you're taking Chem 1A, and that if you're online, you want to download it or print it out. Print out, fill it out, take a picture, send it in, download it like I have. Either convert it into a Google Docs or you can write directly on the PDF if that's your style and then submit that. If you're doing in person, like I assume like me, from what the professor said during the seminar, those in person will be given a handout, and we're going to be filling that out in the lab on next week. So basically, this is standard high school chem early stuff. So I don't know. I'm just gonna go through all of it. You can scrub through the video if you need help. Name, lab section, stuff like that. Basically, name the element. I'm assuming most of you are familiar with the table of elements on page 3. Basically, you just want to go through and find the elements. This does not have the, what is it? The actual name of the element. So you want a more standard table of elements. So I'm going to use the one on my background. Guys don't see it. So basically, first one is Al. That is aluminum 13. We see that here, aluminum 13. Go back, fill that out. Cobalt, basically just going through cobalt, like lead, sulfur, tungsten. I know these off the top of my head. Manganese, barium, and this is antimony, I'm pretty sure, right? This is, yeah, antimony. And then provide the symbol, same thing. Like this is just standard association. This I would recommend going through and try to remember the rough names. So basically all your group 1As, 2As, 3A, 4A, 5A, 6A, 7A, and 8A, your noble gases. And the first, what is it? First row of transition metals, and then silver, cadmium, gold, mercury, and then I don't think I don't think we'll ever need to go into these. And then these are pretty standard. Use uranium, TH is thorium. Like these are weird. I don't think we'll use them often, but there's that. I just realized you guys didn't see the page. So yeah, going back, aluminum, cobalt, lead, sulfur, tungsten, manganese, barium, antimony. Provide the symbol. Basically, you go back. Mg is 12. That's magnesium, stuff like that. Copper is Cu. Tin is SN, I believe. Right? SN is tin 50. Yep. Stuff like that, basically. And then for each species, next is provide the total number of protons, neutrons, electrons, and nuclei present in the species. So, don't quote me on this. I know what protons, electrons, neutrons are. That's basically the amount of the stuff that make up the atom, basically. I'm assuming the nuclei is the total combined number of protons and neutrons. Don't quote me on that. I'm just assuming. So basically, we go to Al. We know it's 13. So it means 13 protons. The atomic number represents the number of protons. The atomic number also, if the atom is, or the element or slash atom is neutral, is also the number of electrons. So we know that this is 13 because it's zero charge. Number of neutrons is different. It is not equal to the number of protons. It is equal to the atomic mass minus the number of protons. So we see here that Al has 27 atomic mass. So we take 27 minus 13. That leaves us 14. So we know that this is 14 right here. And then nuclei, I'm assuming we just add both up. So basically it's anything within the nucleus. So that would be only your protons, only your neutrons. So that's would be 27 because the reason why electrons aren't calculating the weight is because they're just so much smaller in comparison to neutrons and protons, if that's a question you have. Basically go through the same of these. What's something weird? Let's do, I think this is sulfate. No, this is sulfite, sorry. So sulfite, SO3, 2 negative, so we know that this is going to have 1 sulfur, 3 oxygen, and then it's actually have 2 more electrons because it's a 2 minus charge. A minus charge represents you have more electrons because it's more negative. A positive charge means he has less electrons. So basically, a good example for something with less electrons is here. This would have the same number of protons of 13. This would have 3 less electrons at 10 because it's a 3 plus. Same number of neutrons at 14, then same nuclei at 27. So basically, for this one, you would add up the protons, all the protons here. So sulfur, I think, has 32, I believe. S, right? Oh, sorry. Oh, I'm thinking of the atomic mass. My bad. So it would be 16 plus 8 times 3, so that would be 30, if my mental math is correct. 30 here. This would actually be 32 because you have your 2 extra electrons here. And then the neutrons is your combined atomic weight, so it'd be 48 plus 32, that's 70, that's 80. So 80 minus 40, oh, so it just goes out to a nice even, so 40, 40, and then this nuclei would be 80. Sorry, right here, 80, right here. Then down to this part, how many, so basically, yeah, you basically go through the table of elements, look at each atom, calculate the protons, neutrons, electrons, stuff like that, and then combine it with, probably add with a calculator. We're allowed a calculator. If you're want to make sure you use a calculator, I'm going to double check and use a calculator later when I actually do this properly. This is just a rundown. Basically, how many atoms are needed to make 16 molecules. So basically, you want to know the total number of carbons, see atoms, carbons, in the molecule, and then multiply that number by 16. So we know, so for those who don't know, this is how you write a chemical. Basically, we multiply this subscript 3 by the actual total elements in the parentheses. So we have 3 carbons here because it's 1 times 3. Then we have 15 carbons here because it's 5 times 3, subscript times subscript. So we have a total of 18 carbons. So that would be 18 times 16. You can do the math yourself. Total atoms needed to make 16. Oh, total atoms needed. So now we combine the total amount of atoms. Also, just heads up, lowercase. Anything uppercase is its own atom. Anything lowercase is just to help differentiate that atom. Heads up. So this is 1. We know that this is 6 because it's 3, but there's 2 atoms here, so that's 6. And this is 10, 20, yeah, 10, 11, so 33. 33 atoms, so 33 plus 6 is 30, so 40 atoms completely, so 40 times 16. Yep, there's that. How many moles of atoms come together to make 0.5 moles? So how many moles of atoms? If I remember correctly, a mole is, let me double check that. How many atoms are in a mole? That's Avogadro's number, which is 6.22 times 10 to the 23rd. They do not have a superscript here. That makes it weird. Okay, so how many moles of atoms come together to make 0.5 mole? Isn't just half a mole? Give me a second on this, actually. Isn't 0.5 moles? Question? Or is it 0.5 moles times the amount of atoms we got, which was 40? I'm assuming it's 0.5 moles times 40 for that, because that's a really weird question. I don't get that. Giving the oh, okay, this is something I actually do enjoy. Giving the ion carbon dicarbon tetraoxide, so C2O4, 2 negative, 2 minus. What species would you expect to form this following ion? So I'm assuming that this reacts with all these, basically. I'm assuming that, because why else would they give it, right? So since all these are positive, we know that O is the one being oxidized. No, not oxidized. We know that O is going to remain because C2 is the one donating. This is the one getting reduced. So basically, K plus, this would go to, basically you just want to match the charges. Could be potassium oxide. Put as many Ks as you need. Basically, you want to match the charge. I'm pretty sure K. See, this is a weird one because if you guys aren't aware, this means that carbon's donating all. Do I have a pen? Actually, give me a second. I don't have a pen. Because something I wanted to check. Let's see. This is gonna look really scuffed, but basically, if you guys don't know, this is gonna be a Lewis structure. So we have C single bonded. That's 1, 2 atoms. And then we have. Oh, never mind. I'm just okay. So that means 1, 2. 1 oxygen, 1 oxygen, 1 oxygen, 1 oxygen. So it's double bonded there. So it means yeah. And then this has a lone charge here. This has a lone charge here. Okay, so that makes sense. Okay, so what happens? Huh. I'm assuming for. So we're just trying to take the place of the carbon then, so wouldn't it just be. Because for oxygen, it would have to be K2O, because K has a 1 charge. If you weren't aware, I see right here, this group 1A, everything here has a +1 charge. So it'd be K2O, so I'm not sure if they want us to do 4? 4 K2O, so basically, yeah, so we have 4 of this. So 4 oxygen, 8 K plus. That's a thing. I'm not sure. Someone else has done it before. I'm probably gonna ask in class during the lab. And then this is the eighth. What is it? A+3 ion. Would you expect to form? This is even easier. You just want to match up the charges. So you'd have 3 OHs here because that's a single charge. You have to match the +3. I'm assuming they want it to be a neutral ion. S2 negative. You have to cross multiply. So you'd have 2 of these, 3 of this. You can figure out how that's written. And then this matches up directly. So that'd be AlPO4. Convert the units. If you watched Dr. E's videos, you have to remember it's a simple translation of units. And then, yep, that's it. So square units. The video is under Dr. E. It's under the week 0 if you want help with that. Basically, you rough rundown. This is really scuffed. So scuffed rundown is basically we had what 3,500 cm cubed. So basically, when you do a conversion, so it'd be yeah, do I want to do meters? Let's do meters. So do 1 meter. So like cross multi. Oh no, this is so it's like 1 meter over like 100 cm, but like you have to like do that, cube it. So this is all cubed. So then you have like it's like 100 cubed, which looks really weird. They have 3,500 times. It's really weird. Times like 1 over. Because I remember the 1 stays 1. Yeah, like, yeah. Actually, I can just do a double parentheses here. You guys can't see it because I'm on my calculator. Can I just do this? What does that give me? That gives me 0.0035 meters squared. Let's see if I did that right. So we are going to go to Google because Google is our best friend. 3,500 cm cubed. I'm assuming it's going to me 2. Yep. So we got that right. So basically that's what we want to do. And then for the inverse is the same to millimeters. Instead you would do, it's 10 millimeters over 1 centimeter cubed. That's basically how that works. So hopefully that gives you a rough rundown. If there's any specific questions, you can ask me, but I just don't really feel like giving out answers. I know I give a few answers for a few, but yeah. Easiest is to get a quick rundown of this. You want to know all the names of group 1A through 8A. Transition elements, I would recommend knowing the first row, and then silver, cadmium, gold, lead, and platinum. Basically, this whole row, and then these 6 right here. Because I don't think, I mean, tungsten's nice to know, technetium's nice to know, uridium's nice to know. What's ZR actually? Zincorium, that's a metal, interesting. Yeah, so basically, first row, we're mostly going to deal with that. I don't know, it's college, we might actually have to memorize all of this, but just knowing that for now is really good. Then all these groups. So, like for instance, this antimony. It's weird, but you have to remember that. Or arsenic, selenium, tellurium, polonium. There you go. Acetine, iodine, bromine, chlorine, fluorine, neon. Yeah, noble gases. What's Rn? Radon. Yeah, xenon. Stuff like that. So that's basically it. That's your rough rundown. Anyone who needs this video, I'm just gonna put it here. And good luck.